Today I get to introduce to you this cyclotron. A cyclotron is among the large instruments used in nuclear chemistry. Basically, it's a particle accelerator. However, the particles are not accelerated in a straight line, but along a circular path. The particles being accelerated are ions. In this case, different ions can be accelerated, like protons, deuterons or alpha particles are typically accelerated in such a cyclotron. Yes, I am talking about protons and writing H- here. I'll explain why in a minute. Let's start with a setup. In the middle you have the ion source. Let's say our particle is a proton. In our case today, it's actually accelerated as a hydride or H-, but unfortunately this simulation doesn't account for this. At the acceleration electrodes, which are semicircular metal containers, a high frequency generator applies a voltage. One of these plates becomes the negative pole, attracting the positive proton. The two acceleration plates are situated in a magnetic field. Under the influence of a magnetic field, the proton moves in a spiral path. Corkscrew or right-hand rule for negative charge carriers, if you remember this rule from physics class. Anyway, the polarity needs to be reversed as soon as the hydride completes its path through the first acceleration electrode. With each acceleration, the particle moves faster. Wow, what a revelation. But this also means that the circular path gets larger. This phenomenon, where the particle moves faster, resulting in a larger orbit, but takes the same amount of time for the now larger orbit, is called the cyclotron frequency. Eventually, the accelerator comes to an end, and using a deflection plate, the particle is ejected straight out and hits the target. I will link an excellent explanation video in the video description. You can also calculate the angular velocity based on mass, charge, speed and magnetic flux density, but I will cover that in another video about calculations in nuclear chemistry. So, what's the purpose of such a device? Well, to accelerate particles and then to carry out nuclear reactions. First, let's cover some basics about nuclear reactions, as I'll be using the technical terms quite frequently in the next few minutes. A radioactive decay can also be described in a nuclear reaction equation, but that's not our main focus today. Much more important is the targeted production of specific isotopes. So not enrichment where existing isotopes are separated, but the actual creation of isotopes that were not previously present in the material. You start with a target, the base nucleus, and then bombard it with a projectile. Possible projectiles in our case are protons, deuterons or alpha particles. This results in a nuclear reaction, and in the end you will have an ejectile or the emitted particle and the residual nucleus. For example, in the production of fluorine-18, a proton is the projectile and it's fired at oxygen-18, our target. A nuclear reaction occurs and the residual nucleus is the fluorine-18, with a neutron as the emitted particle or the ejectile. Yes, in the chart of nuclides we briefly encountered fluorine-19. This is produced as a compound nucleus, and explaining further details would take us a bit too far. I will cover that in another video. Since protons with an energy of 30 mega electron volts hit our target and produce incredibly intense activities, everything is monitored around the clock. Just take a look at this thick lead door. The door that you see here leads to a room with the solid target. We'll go through the other one for now. Let's start from the very beginning. This blue component is the alpha ion source. A closer look shows that helium gas is injected and fully ionized here. It's a plasma ion source. The helium ions are then transported via the beamline up into the cyclotron, located at the moment just above us. And then they can be accelerated. On the other side, there is another ion source for deuterium and hydrogen. So again, H2 gas or D2 gas is used. Electrons are added and then you will end up with H- or D- for acceleration. These three cylinders are turbomolecular pumps. The ions are transported via a beamline into the center of the machine. This is where the actual acceleration happens. Hydride and deuteride ions can be simultaneously accelerated in what's called a dual beam mode, and then can be extracted at both exit ports. When irradiating with alpha particles, the magnetic field needs to be switched because we're changing from negative to positive. So the accelerated particles shot out of the cyclotron through the beamline into the target. Wait a second, it's not that simple. You remember the image from the beginning of the video? This is what the deflector looks like. It contains tungsten, molybdenum, copper and some other fancy elements, ensuring that the alpha particles are ejected into the right direction. A dosimeter was just held against it because even such components become activated and radioactive. Now the accelerated alpha particles have been pushed out by the deflector and then hit the bending magnet, which theoretically has 5 positions. 2 of them are currently in use, one directing the beam here and one the other way there. If you are accelerating H- ions, a stripper foil is required to strip away the 2 electrons. The negative ions are used for accelerations due to this dual beam mode, but the actual irradiation happens then with positive ions. Of course, there has to be a control unit for this stripper foil. Everything happens in a vacuum. Earlier we saw 6 turbomolecular pumps, but there are also some oil-sealed pumps and cryopumps. Now let's move on to the liquid and gas targets. On the respective line, only deuterons or protons can be used for the irradiation. Alphas are only used with solid target, which we will look in shortly. These blocks here are quadrupole magnets, which are used to deflect or rather to focus the beam. They have to be water-cooled. The bending magnets directs the projectiles to either the liquid or the gas targets. Only one of these 5 targets can be irradiated at a time. We have the large water target, which holds about 3 milliliters of liquid, and then next to it the smaller water target, which has a volume of about 0.7 milliliters. Then there is the operation target used to check the beam. And next we have gas targets for producing oxygen 15 and another one for producing carbon 11. First, let's take a look at the liquid targets. I said water targets earlier, but this isn't regular H2O. It's heavy water. But it's also not D2O. It's another form of heavy water. It's oxygen 18 enriched water. So it's heavy not because of the 2 extra neutrons at the hydrogen, but because they are at the oxygen atom. From this small glass container, 3 or 0.7 milliliters of oxygen 18 enriched water is drawn. At least 50 milliliters of oxygen 18 water enriched to 98% is needed. Just to give you an idea of how expensive that is, look here. This is then pushed through the capillary. The 3 milliliter column isn't further subdivided. At this stage, the water is not active yet. By the way, it's transported using gas. In the capillaries, there's helium in front and after the water column. Now, protons hit the oxygen 18 and via a PN reaction produce fluorine 18. I only illustrated 1 proton, but in reality, a synthesis run can yield 40 gigabecquerels of fluorine 18 after 10 minutes at a beam current of 80 microamperes. Microamperes is a common exam pitfall. We are more familiar with amperes in the context of electron flow, but it actually refers to just the flow of charges, and it also includes the positive charge of protons or deuterons. The fluorine 18 exists as fluoride ions in the still unreacted water, and is then distributed through these very thick capillaries and switching valves into the lead-shielded cells of various in-house laboratories. Now for the gas target. One of them is oxygen 15 and one of them is for carbon 11. For oxygen 15, there are various methods. The gas lines for the projectiles or the targets look something like this. For instance, there is a line with 99.9% pure deuterium gas for deuteron irradiation, and another one with 99.999% of pure hydrogen for the proton irradiation. For carbon 11 production, there is nitrogen gas with 0.5% oxygen. Here the nitrogen is bombarded with protons, and in a P-alpha reaction resulting in carbon 11, which then combines with the added oxygen to form carbon 11 CO2. The oxygen is 99.99% pure, while the remaining 99.5% volume of the gas is nitrogen, which is 99.9995% pure for mix number 1, for example. Oxygen 15 is produced from nitrogen 14. For this, nitrogen is bombarded with deuteron ions and in a DN reaction produces the oxygen 15. This can either be extracted as oxygen 15 oxygen gas, as described here, or mixed in CO2 to allow transportation as oxygen 15 in this form. The activated gas is then released and transported to the lead-shielded cells. Now let's move on to the solid targets. For beam diagnostics, there are also some rods to check whether the beam is centered and has the correct size and shape, etc. A proton beam is directed out and focused through additional quadrupole magnets in the beamline. We are now in the adjacent room. For the beam diagnostics mentioned earlier, a camera is used and it's connected via a periscope to prevent it from being destroyed by the radiation. Here we have a VHT shutter which separates the high vacuum of the cyclotron from a much lower vacuum behind it. It's maintained by an oil pump. What we're seeing here right now is a 4-sector aperture. It can shape the beam to fit perfectly onto the target. This is checked by using paper. By firing 1 microamperes of protons, deuterons or alphas onto the paper for 30 seconds, the burn mark shows whether the beam is properly aligned or not. In this case, it wasn't. Both the software and these parts of the hardware are custom built, requiring top-notch workshop skills that I can't even fathom. With this software, everything can be controlled from vacuum systems to hose cleaning and compressed air. Solid targets are clamped into these copper holders, and after irradiation, other components, including the quadrupole magnets, are also become activating, reaching up to 70 microsieverts an hour or nearly half a millisievert per hour at another beamline. This footage was taken on a Monday, so not much irradiation happened over the weekend. Looking inside such a beamline, you can also see the 4-sector aperture. The target can then be reattached, vacuum be drawn, and then irradiated again, but only after everyone has left the room. I hope now we have a better understanding on how a cyclotron looks and how it works. This video was recorded at the Research Center in Jülich in the Institute for Neuroscience and Medicine under the direction of Professor Dr. Bernd Neumeier. The Nuclear Chemistry Cologne is a collaboration of the University Hospital Cologne, the Research Center in Jülich and the University of Cologne. A special thanks goes out to Stefan for the tour and the explanation, and of course to my patrons. With that being said, thank you for your attention and goodbye.